Hello students, welcome to another episode of All Force e-learning program. This is session number 13, right? So in this, today we shall learn about an electric dipole. Our today's topic is electric dipole. Now before going to this topic, let's have a preview of what we have learned in the earlier classes there. So I was telling you, electricity, the study of various effects of charge. Charge is a fundamental property of matter which exerts a special force called electric force, right? Charge is measured in coulombs, SI unit coulombs, CGS unit stat coulombs. It's a physical quantity. It's not a fundamental quantity. It is a related quantity, and it's a scalar. Its dimensional formula is IT, current I into T. Then the methods of producing charge on a body, giving charge to a body, is electrification. There are three methods of electrification: charging by friction, charging by conduction, charging by induction. Three methods. Later, force, actually, the property of charge was observed by the people because of this force that is being executed by the charged bodies. When this special property attained by the bodies, they exhibit force of repulsion and force of attraction. Like charges repel, unlike charges attract. The mathematical form of this was given by Coulomb's law. Force is directly proportional to the product of the charges and inversely proportional to square of the distance between them. Force is 1 by 4 pi epsilon 1 q and q2 by r square. This is force. In air it is 1 by 4 pi epsilon naught. In the medium 1 by 4 pi epsilon, or 1 by 4 pi epsilon naught into k. It is k times less. Force in the medium is k times less than force in air. Right? Similarly, next, principle of superposition. When there are many charges, the force on one charge is the vector sum of all the individual forces, all the forces acting on that charge. Right? Next, the field, concept of field. Every charge produces field around it, and it interacts with the charges within that field. Space around the charge where the effect of the charge is felt is electric field. Electric field intensity. Next, it is the force experienced by a unit positive test charge placed at point in the field. Field intensity. Later, field due to multiple charges. Again, the principle of superposition is applied there. The resultant electric field at any point is the vector sum of all the individual electric fields at that point, considering all of them simultaneously. Right? So this way we have done these topics. Now our next topic is electric dipole. Now let us have a keen perception regarding this. Let's go in detail. Dipole in general. Dipole means two poles, two equal and opposite poles separated by some distance. Dipole in general. Now it is electric dipole, charged dipole. So it is a combination of two equal and opposite charges. There are two equal and opposite charges, plus q and minus q, separated by a distance. The system of equal and opposite charges separated by a small distance, separated by a small and finite distance, is called as a dipole. An electric dipole. It is a system of two charges, equal and opposite charges, unlike charges, separated by a distance. Right? This is called as an electric dipole. It is analogous to a magnet. You know, a magnet also has north pole, south pole, separated by some distance. A magnet. This is analogous to a magnet. North pole, south pole, separated by a distance. The poles, the ends. Dipole is two poles, two opposite entities, two identical and opposite entities separated by some distance. Right? So here electric, charged. In electricity, the fundamental property is charge. So two equal and opposite charges separated by a distance is termed as electric dipole. Same as magnetic dipole. Magnet has north and south pole. Here positive and negative charges separated by a distance. This is called an electric dipole. In nature, in physical, the physical significance, if you go upon, we find some molecules some molecules where positive charge, negative charge. Let's say sodium chloride, Na plus Cl minus. Na plus Cl minus, right, separated by some distance, they act as a small tiny dipole. Water molecule, H2O, two oxygen molecules and one hydrogen separated by some distance, they behave as a dipole, right? So this way there are certain, in nature also we come across certain things where they behave as electric dipoles. So electric dipole is a combination of two equal and opposite charges separated by some small and definite distance. This way it is. Now when I consider the distance between them, the midpoint between them is this point. Let's suppose it is O. Now this distance is taken as A, and even this distance is taken as A. The total distance between them is 2A. Total distance is 2A. Now why like this? Why? Because in a electric dipole, actually in electricity we are dealing with some mathematical formula, like analytical formula, F is equal to Q1 Q2 by D square, electric field 1 by 4 epsilon Q by D square. So when we have to take that value of distance for this dipole, from where you have to take the distance corresponding to the point where you have to find the field. For example, you have to find the field at a point. Then what distance D to the point, from which charge? Is it from this charge or this charge? No, we have to take it from the midpoint between them. Actually it is assumed to be the origin, and these two are separated by two equal distance on either sides. Midpoint, all distances are measured from this midpoint. So this charge is at a distance A and this charge is at distance A. They are separated by equal distance away from that origin, from that point, right? So the total length is 2A. You know, this is the length of a dipole. Dipole, electric dipole length of dipole, it is a vector quantity. It's a vector. So length of the dipole L bar is a vector. It's 2A, a vector. It's 2A vector. It's a vector quantity. The direction is from negative charge to positive charge. The direction of the dipole length, direction of length of the dipole is a vector. Length of dipole is a vector, and the direction is from the direction of length of the dipole is from minus q to plus q. Even in magnet also, the length of the magnetic length, the length of the magnet is a vector. It's a vector quantity, and the direction is from south pole to north pole inside the magnet. Here also, from negative charge to positive charge. It's a vector. Please make a note of this, right? So electric dipole, it is a combination of two equal and opposite charges. A system of two equal and opposite charges separated by a small and finite distance is termed as a dipole. Right? So a dipole has two charges separated by some distance. Now strength of the dipole, the mathematical factor which defines the strength of the dipole. The strength of the dipole is measured by a quantity called electric dipole moment. Electric dipole moment. You know, first year we have learned moment. Moment is turning effect. Actually a dipole, when a dipole is placed in a electric field, then this doesn't stay at rest. It executes, oscillates. It has a turning effect. The measure of the turning effect, that is measured by the strength of the dipole is given by electric dipole moment, represented as P bar. Electric dipole moment represented as P bar. This is the strength of a dipole. So a dipole is a combination. The combination of system of two equal and opposite charges separated by a small and definite distance, fixed distance. Right? Now, sometimes we'll be coming across a term called ideal dipole. Now, what do I refer? How do I mean ideal dipole? An ideal dipole is termed as the combination of two equal and opposite charges separated by a small distance. The distance is very much small, but the magnitude of the charge is very large. That is, each charge has high magnitude of charge. Plus q minus q, the magnitude of the charge is very much high, but the distance of separation is very small. And this is termed as an ideal dipole. And you know, the ideal dipole is represented by an electric symbol called like a bold arrow like this. A bold arrow is a symbol for an electric dipole, right? The direction of the arrow, this represents arrow, the direction. Here it is minus q charge, it is plus q charge. The direction of the dipole moment is from minus q to plus q. The direction of the length of the dipole is from minus q to plus q. So it is represented by a bold arrow. It is an ideal. A short dipole, actually in simple, in general, it is a short dipole. Actually technically it is an ideal dipole. So an ideal dipole is a combination of two equivalent opposite charges of high magnitude. Charges of high magnitude separated by a very small finite distance between them. Separated by a very small distance. Now that is an ideal dipole, represented like this. You come across in some books with a dipole represented like this. Now in this one, the arrow represents the direction of the dipole moment. Rather, the arrow represents the direction of the length of the dipole. It means at this end there is minus q, at this end there is plus q. Now this you have to remember, an ideal dipole, right? Okay. Now coming to the mathematical part, analytical part of it, the strength of the dipole, the stability of the dipole, how much turning effect it shows. Now that is defined by a term called electric dipole moment. You know, electric dipole moment is defined as, right? It is defined as the product of, it is the product of either of the charges. So a dipole has two equal and opposite charges, same magnitude, opposite. So take any of the magnitude, one magnitude, any magnitude q times the length, either of the magnitude of the charge and the length of the dipole, that is 2a. In this one, 2a is a vector, so this is a vector. So electric dipole moment is the product of either of the charges in the dipole and the separation between them. The separation between them, the product of these both is called electric dipole moment, P bar. It's q into 2a bar. So dipole moment, it is similar to magnetic moment in magnetism. Every magnet has got its own strength exhibited by a term called magnetic moment. Now magnetic moment, what is magnetic moment? It is the product of the pole strength of any of the poles and length of the magnet, right? Product of the pole strength and length of the magnet. So similar to that, electric dipole moment is the product of any of the charge, either of the charge and the separation between them, the distance between them. So this is dipole, electric dipole moment. So P bar is 2aq, right? This is the magnitude. Actually this is a general definition. Actual definition is defined in a coming topic where the dipole is placed in a field. When it is placed in a field, it experiences couple torque. Now by that we define the actual definition comes there. But in general we can define as the product of the charge and length of the dipole. So P bar is 2a into q. Now its units, it is measured in CGS system, it is measured in distance into charge. Charge we know it is measured in ESU into distance is centimeters. ESU centimeter or stat coulomb into centimeter. Stat coulomb into centimeter. This is the CGS unit there. CGS. In chemistry they define this as dBA. DEBY dBA. In chemistry they take the unit as dBA. CGS, simple, right? CGS unit. But in SI system, this is defined as the distance is in meters, charge is coulombs. Coulombometer, it's cm, coulomb meter. In SI system it is coulomb meters. CGS system, it is defined as stat coulomb centimeter, dBA it is. And in SI system it is coulomb into meter like this. The conversion, 1 coulomb meter is equal to how many CGS units? 1 coulomb into meter. We know, we have learned while talking about the units of charge. 1 coulomb, SI unit is coulomb, CGS unit is stat coulomb. 1 coulomb is 3 into 10 to the power of 9 stat coulombs. Stat coulombs. So 1 coulomb is, this is capital C, please don't get confused, capital C hyphen M. So coulomb is 3 into 10 power 9 stat coulomb into meter. Meter is 100 centimeters. So 1 coulomb meter is 3 into 10 to the power of 11 stat coulomb into centimeter. But this is dB. So 1 coulomb meter you can write as 3 into 10 power 11 dB. CGS units. Units conversion. SI unit and CGS unit like this. Next, it is units like this. It's dimensional formula. Coming to the dimensional formula of dipole, electric dipole moment. It is charge times length. So mass m power 0, L power 1. Charge, we know charge is ampere into time. I is equal to Q by T. Q is IT, ampere into time. So it's T power 1, I power 1 it is. So its dimensional formula is M0, L1, T1, I1. Dimensional formula of electric dipole moment. This is the definition. The product of either of the charge and length of the dipole is called electric dipole moment, represented as P bar. So charge is Q, length is 2A, it's 2AQ. The formula for electric dipole moment. Its CGS units, it is charge is stat coulomb, ASU into centimeter, stat coulomb centimeter dB, and coulomb meter like this. 1 coulomb meter conversion into CGS units is 3 into 10 power 11 dB. And its dimensional formula is M0, L1, T power 1, I power 1. Next, it is a vector quantity. It's a vector quantity. Vector quantity. Charge is a scalar, but dipole moment is a vector quantity. A vector quantity has direction. Now, what is the direction? Its direction is same as the direction of the length of the dipole. Like I was telling you, length of the dipole is from minus Q to plus Q. Even the direction of the dipole, if it is minus Q charge and plus Q charge, then the direction of the dipole moment is from minus Q to plus Q along the line joining them. Like this. So direction, it's a vector quantity. So these are the units, these are the this is conversion, its dimensional formula, and its vector quantity showing its direction like this, right? So electric dipole, a dipole is a combination of two equal and opposite charges separated by a small and finite definite distance. It's a system of two charges together, a set. It is a set of two charges like this, right? This is dipole, and this dipole has its own effect in the field, or how much effect does it show? This is measured by a quantity called electric dipole moment, P bar. It is the product of either of charge, any one of the charge you should take the magnitude Q and the distance between the charges, the length of the dipole, charge into 2AQ. This is the formula for the electric dipole moment. Units, coulomb meter, SI unit, CGS, stat coulomb meter, and dimensional formula L1, T1, I1, M0, and it is a vector quantity. Its direction is from minus Q charge to plus Q charge along the line joining the charges there. Okay, so this is dipole moment. Next, in nature we come across certain molecules which exhibit dipole moment, and there are even some molecules which do not have dipole moment. Let us have a understanding regarding this. The molecule whose center of the positive charge and the center of the negative charge coincide with one another. There are some molecules whose center of the positive charge and center of the negative charge coincide with one another, right? There is no separation between the center of positive and center of negative. Such molecules are called non-polar molecules, and these non-polar molecules do not have any net dipole moment, so they do not possess any dipole moment 0. But however, when they are placed in an electric field, when you place them in an electric field, then the positive, center of the positive and the center of the negative are separated due to the presence of the electric field. Due to the presence of the electric field, the center of the positive and negative, positive is attracted by this negative charge, negative attracted by positive, they move apart. Then they behave as a dipole and show some electric dipole moment. So such molecules are called non-polar molecules. Non-polar molecules. In general, we come across in our environment, we come across substances, various compounds, various molecules which exhibit different property regarding this. There are certain molecules, I was telling you, whose positive and negative, the center of the positive and the center of negative coincide with one another, right? They coincide. Then there is no separation between their centers. Such molecules do not possess any electric dipole moment. These molecules are called non-polar molecules. Non-polar molecules, right? Example CO2, CH4, etc., so on and so forth. So such molecules do not actually possess any net dipole moment alone, but when they are placed in a uniform electric field, then the molecules, the center of the positive and center of negative, get separated by a small amount. Then they show some net dipole moment. So such molecules are non-polar molecules. But there are some molecules who, in the absence of the electric field itself, possess dipole moment. The center of the positive charge of the molecule, center of the negative charge, right, they are separated by a small distance. They originally possess dipole moment. Such molecules are termed as polar molecules. Such molecules are polar molecules. Example, H2O, NH3, etc., etc. These molecules, the net positive charge of the molecule is concentrated at one point, net negative charge is concentrated at another point with a small separation. And such molecules initially possess dipole moment with separation and charge. Such are called polar molecules. Now again, when they are placed in a electric field, they still get separated, their dipole moment increases and they show turning effect, etc., various things. So with respect to dipole, all the molecules are classified into two, right? Polar molecules and non-polar molecules. Non-polar molecules are the molecules where the center of the whole positive charge of the molecule and the negative charge of the molecule coincide with one another, and there is no separation between there. Net dipole moment is 0, right, in the absence of the electric field. But however, when they are placed in electric field, they get separated, show some dipole moment, show some turning effect. So in the absence, they do not possess any dipole moment. They are called non-polar molecules. Example, carbon dioxide, CO2, ammonia, NH4, etc. Methane, CH4, etc. Now coming to another type, the molecules, in the absence of the electric field itself, the molecules have the center of the positive and the center of negative separated by a small distance. They initially possess some separation. They initially possess dipole moment. So net dipole moment do exist. Such molecules are called polar molecules. And when they are again placed in an electric field, their dipole moment increases, separation increases, they show bigger effect of the things there. So molecules are classified into two, polar molecules and non-polar molecules. And we even come across some molecules where it is a combination of two dipoles. Like for example, suppose if it is minus 2q, this is plus q and this is plus q. It's called as a quadruple. A quadruple is a combination of two dipoles. We come across molecules like this. Example, water, oxygen O, hydrogen and hydrogen. right? Separated with some angle between them. So this is one dipole, this is another dipole. We come across such molecules, many molecules as such we come across in our daily life. So it is a combination of two dipoles, quadrupole. There are molecules which are combination of many dipoles together like this. So quadruples with some angle between them. It's minus q plus q minus q plus q, existing in any form, with any angle between them, right? Such a combination. And suppose there are molecules, there are compounds like this, plus q minus 2q, and this is plus q. Even this is a quadruple. Of course the net this thing becomes 0, but this is also a quadruple. There are quadruples of different shape. A quadruple of this shape, it's minus q plus q minus q plus q, right? Combination in this manner. Even this also a quadruple. So this way we come across molecules which are combination of dipoles. 2 dipoles, 3 dipoles, many dipoles together like this, right? So if 2 dipoles combine together, it's called as a quadruple. A quadruple is something existing like this. 2 dipoles separated by a small distance. Such things are called quadruples. Combination of dipoles with any angle between them. Sometimes the angle can be more the acute angle or obtuse angle, even a right angle also, or even they are linear molecules with, right? I have shown a linear molecule with plus q minus 2q and plus q, right? So this way combination molecules with combination of dipoles. Many dipoles, some dipoles combined together, or many dipoles together form a quadruple. 2 dipoles together form a quadruple. Recently there was a interesting question based on this asked in one of the entrance examination. Net dipole moment of a quadruple, combination of 2 dipoles at an angle. So this way we have to consider the dipole moment of one and the other, considering them as a vector, then add vectorially. Apply Parallelogram law of vectors. R mod R is root of a square plus b square plus 2ab cos theta. Net dipole moment you can find out, right? So we come across such things in our daily life, different molecules of different nature. So electric dipole, so I was telling you, dipole is a combination of 2 equal and opposite charges separated by a finite definite small distance, right? That is electric dipole. Same as magnet. A magnet also has the same thing. And dipole moment actually it is the physical quantity, the measure of the strength of dipole, characteristic of a dipole. That physical characteristic, the measured characteristic of a dipole is given by a quantity called electric dipole moment. Dipole moment, it is a product of the charge and the separation. The more the separation, more the dipole moment, and the bigger charge, more the charge, more dipole moment. An ideal dipole or simply a short dipole, it is a combination of 2 equal and opposite charges of more magnitude. Charge of more magnitude, but separation between them is very small. Charge of more magnitude, but the separation is very small. Such thing is called as a ideal dipole, or it is simply a short dipole, right? Dipole moment, product of the charge and the separation between them. P bar is q into distance between the charges t. Q into d, right? Dipole moment. It's a vector quantity. The direction of the dipole moment is same as the direction of the length of the dipole. Dipole moment and length of dipole both are parallel vectors. Equal. I mean they are in same direction. And charge dipole moment has units coulomb meter. A CGS unit is TP. Dimensional formula L1 T1 I1, and it's a vector quantity. Molecules, with respect to dipole waves, molecules are classified into 2: polar molecules, non-polar molecules. Polar molecules, in the absence of the electric field, they possess electric dipole moment. Non-polar molecules, in the presence of the electric field, they show dipole moment, but in the absence of the electric field, they do not possess any dipole moment. They are called non-polar molecules. Non-polar molecules, example methane, carbon dioxide, etc. Polar molecules, water, ammonia, etc. Right? Next, Coming to a quadruple. A quadrupole is a combination of two equivalent two diodes combined together form a quadruple, right? With any angle between them. Two dipoles either parallel at some acute angle, right angle, obtuse angle, or opposite. Then the combination of this is called as a quadruple. Many dipoles combine together to form different combinations. Combination of two dipoles will be called as a quadruple, right? So this is the concept regarding electric dipole. Thank you.